Okay, so I believe this is the page we're at. There are notes. Yep. Yeah, Michael.
Quiz, it's just on 7 and 8. There's anything from the other chapters?
The quiz, end of chapter 6,
Okay.
7 and 8. Yeah. Just on those. And as it gets a little closer to then, we might talk a little more specifics about that too. Alrighty. So we were talking about how both light and electrons are similar in that they have wave-like properties and particle-like properties. And it's not that it even really sort of switches from one to the other. It's that they're kind of both at the same time. And the even better explanation is that they're actually neither. Okay? Particles and waves are metaphors that our puny minds can use to explain parts of light and electron behavior. But in actuality, they are what they are, and their strange behavior doesn't lend itself exactly to some kind of physical metaphor that we can describe them by. So the best we can do is understand that the wave and particle natures of the electron are there together, but they're actually complementary, which means the more we know about one, the less we know about the other. Okay? We can't know everything about both the particle and wave natures at the same time. And specifically, the more precisely we know one, the less precisely we know the other. And that's what the Heisenberg uncertainty principle is. The position of an electron comes straight from its particle nature. There is no position of a wave. Okay? A wave is just a wave. There's no point to it. Okay? So if there's any kind of property of an electron that has to do with it being at a certain point, that's a particle-like property. But the momentum of an electron is actually more of its wave nature. Okay? That has to do with more of direction and the kind of the way it's going. But it's impossible to know both of those precisely at one time. So there's it's a complicated looking equation, but it's actually fairly simple. This delta x, just write uncertainty in position. Right? Mass times velocity is one way of doing momentum. So m delta v, right? That would be the change there. That's the uncertainty in momentum. So uncertainty in position times uncertainty in momentum. When you multiply two things like that, what sort of relationship do they have? Are they directly proportional or inversely proportional? Or what do you think? Like think of P times V in the ideal gas law. Anytime you're multiplying two things and it's equaling some kind of constant like that, if one of these were to increase, like if we had a huge uncertainty in position, we would have less uncertainty in momentum. Okay? And thought of that a different way, if we had less uncertainty in position, that means we know exactly or fairly close where an electron is. The uncertainty in its momentum goes up, so we don't know where it's headed. Okay? So this just greater than equal to, that's a constant, but that sort of sets up the lower limit of how well we can know both the uncertainty and position. So that's really all you need to know about that. We'll come back to that a couple of times, and that the better we know one, the worse we know the other. It's an odd property that electrons have, but that's what the Heisenberg uncertainty principle is. So what's the use of it then if we can't know position and momentum at the same time? What can we know? Quantum mechanics does allow us to calculate the probability of an electron behaving a certain way. And that's entirely what we go off of now when we're talking about electrons, what the probability of an electron behaving a certain way is. Okay? So a wave function, that's a Greek psi, psi, I think. That's the symbol for wave function. A wave function is a mathematical equation that describes the wave-like properties of an electron. Okay? It's a very complicated equation, and the more complicated the electron gets, the more complicated this equation gets. So thankfully, we don't have to deal directly with wave functions, hardly at all. Okay. Quantum numbers are 4 of the variables in the wave function, right? Equations can have variables to them. It's a big, long equation. There are variables, places where you can enter digits. Okay? And those quantum numbers are 4 variables that combined are used to describe a particular electron. So any given electron will have these 4 quantum numbers, which are essentially like coordinates that describe about everything that we need to know about each of those electrons. And we're going to talk about what those quantum numbers do here in a second. So the wave function is the equation. The quantum numbers are the variables that get plugged into that equation. And an orbital is a solution to a wave function with a certain combination of quantum numbers. So that equation will output sort of the answer to that equation with particular quantum numbers inputted into it. That's an orbital. And what that solution actually looks like is a 3-dimensional volume. Okay? It could be a sphere, or it could be a more complicated shape. But essentially what that volume is telling us is that's the volume inside of which an electron is likely to be found by a certain probability. Okay? So the wave function is the whole equation that we don't have to worry about. It's a very complicated equation. Quantum numbers get plugged into that equation, and the result that it spits out is an orbital. Okay? So the orbital for a particular electron will depend on the quantum numbers for that electron, because the quantum numbers are what are used to describe that electron. Okay? So